Let's look at the physical mechanisms that involve in a pool boiling, which is the boiling of a stationary fluid. Stationary liquid. So we have different boiling regimes that I would like to talk. And there is another thing that we called boiling curve. So in one of the early works in 1934, Nukiyama, he was doing experiments, and what he noticed that the way that he was doing experiments, like he had water here, and then he was running a wire here that he could control, an electrical heater, I would say, similar to or then he could control the Q that is going through that, and he could measure the temperature of that one. And what he noticed here is there are going to be different flow regimes or different boiling regimes depending on this delta T excess. So delta T E Ts minus T sat. So it depends on the magnitude of that, we can get different boiling regime. To illustrate that, let's say we have this container that we are heating from the bottom. And let's assume we have water in this container. So we have water, and if it is 1 atmosphere, the Tsat is going to be 100 degrees C. So this is Tsat. Okay, let me just write it down out. So Tsat is 100 degrees C. Now, if we increase the surface temperature, the bottom surface temperature, let's say to 103 degrees C, okay, slightly over the saturation temperature, what we are going to see here is the water close to this surface is heated up, but really there is no bubble formation. So this hot this heated water, because of the change of the density decreased, so we would have some sort of convections that is occurring here. So we would have some rise of the heated water and then replacement of that here. So this is what we call as a regime natural convection boiling. Natural convection boiling. And generally that happens in a small excess temperature. So delta T is less than 5, greater than 1. So that's the regime. So there is really no bubbles, and liquid is slightly supersaturated here. And then we have rise. Evaporation mainly happens because we have these circulations and rises to the free surface. That's the first one. Then if we increase the surface temperature, so we have the container still heating. Now, if we say the temperature is, let's say, reaching 210 degrees C, then what we are going to see here is formation of bubbles here. So we're going to see bubbles are forming at the surface. Initially, when these bubbles are getting released, they are getting dissipated and disappear. But if we further increase the temperature, slightly increasing the temperature, like let's say if the delta TE is between 5 to 10, then what we are going to see here is this bubble formation, but as the bubbles just detach, they are going to dissipate it. But if we go above, like let's say delta T excess of 20 degrees, then what we are going to see here is we are going to see some columns. So these bubbles are just rising up, and we are going to see a rapid formation of these bubbles that are just rising up and everywhere. So what we call this one, and again we have vapor phase going to the outlet. So this is what we called nucleate boiling. And I will talk about the characteristics of that in a second. The third one is if we further increase the temperature, so let's say the temperature is now 180 degrees C. Then what we are going to observe here is formation of bubbles. Bubbles are going to be formed, but we are going to see a lot bigger bubbles here at the surface. Some of these bubbles are just growing at the surface, and so these are, let's say, the bubbles here that we have, and covering the surface, part of the surface, and that's what we call transition boiling. The transition boiling happens after the nucleate boiling is delta TE between 5 to, let's say, 30, and then when we have, let's say, delta TX is around 120 greater than 30, we have this transition boiling. And if we further increase the temperature here, the temperature of this surface, then let's say to 400 degrees C, yes, 400 degrees C, then what we are going to see here is a blanket of vapor is forming at the surface. So if I just show it with different colors here, say orange. So these are the pocket of vapor for the transitions, but then we will see a blanket of vapor is forming here, or a film of the vapor is forming here, and that's what we call film boiling. And the surface is completely covered with the stable film here. Now, if we bring these regimes into a curve or plot, the flux that we are providing. So let's say if I make a plot of Q double prime S in the form of watt per meter square, and versus delta X is delta temperature difference Ts minus T sat here, starting from, let's say, 1 degree up to 5 degree. Let's put it in the log scale. So let's say this is 10, 100, 1000 here. Then it's gonna be 120. Say this is 30. So what we are going to see here is as we're providing more heat, the temperature of the solid, the difference between solid and saturation is going to increase till we reach to 1 point to the 5 degree, and then we would see more increase into that till 30 when we reach to a maximum, and then we would have a rapid decline in the flux, and again we would have a rise here. Okay, so this is what we called boiling curve. I'm just going to put it here. We call it boiling curve, and there are various points that we distinguish here. So this, let's say this is point A, point B, C. No, actually there is another one. Yeah, this is 10. So this is B. C. and then D. Let's label that by this point. So between 1 and 5 degree, this is where we have, as we talk, natural convection boiling. Then between 5 and 10, what we have here is the nucleate boiling, but there is really like bubbles collapse in liquid, so we don't have a lot of bubble in the liquid. Let's call everything here between 5 to 30. Let's call here, this is nucleate boiling. And nucleate boiling, we have two different regimes that can happen. So here, the regime that bubbles collapse in liquid, condenses back in the liquid, and in between 10 and 30 is the place that we have bubbles rise to the liquid free surface at the top. So these are the two parts of nucleate boiling. Between 80 to 150, this is where we have transition boiling, and above hundreds, what we have is film boiling. So this is the boiling curve, and I'm plotting that for water. If you are looking at the water, so the flux is going to be, let's say, 10 to power 3, and it's almost 10 to power 6 here. So let's say this is 10 to power 4, 10 to power 5. What we would get for different sort of liquids, the same graph, the same boiling curve that I'm showing here. Now let's look at each of these zones and look at the characteristics of each of them. So the first one is from 1 degree to A, and that's what we called natural convection boiling. So point A is natural convection boiling up to point A. So in this natural convection boiling, what we have is the water close to the surface is slightly supersaturated. So water solid surface is slightly supersaturated and evaporates. This water evaporates when it rises to the free surface. And heat transfer from the solid surface to the bulk liquid is by natural convection. So we have transfer from surface to fluid by natural convection that we have seen before, and there is no bubble formation. And this regime generally lasts as long as this delta T excess is between 1 and 5 or less than 5 degrees C. Let's just put it there. So this is in terms of natural convection boiling. Nothing really exciting here. Then the other one is nucleate boiling. And that nucleate boiling in the graph is from point A to C is where we have nucleate boiling. So from point A to C in the graph. So the first bubble, when we reach to temperature of 5 degrees for water, or this point A that we are passing the natural convection, first bubbles are appearing at point A. So I'm going to just write it down. First bubbles form point A. So at some random spot or some spots from nucleation site around, like at the solid surface, you would see this these bubbles are forming when delta T excess reach to the point A, and that's what we called onset of nucleate boiling, or ONB. So this point A is also called ONB. So this is the onset of nucleate boiling that we have here. That's for point A. Then when these bubbles are forming, we are between point A and B, that the delta T excess is less than 10 degrees C, greater than 5 degrees C. As we discussed, we have isolated bubbles are forming. Bubbles are formed at the solid surface or surface heater at various nucleation sites on the surface. Now, these bubbles, if they are getting detached from the surface, or maybe while they're at the surface, are dissipated. So bubbles are, or they are condensed in the liquid. The liquid shortly after they separate from solid surface. So the bubbles are formed, and then they are quickly dissipates, and this process creates some stirring and agitation. So stirring and agitation. Agitation caused by entrainment of the liquid to the heater surface. This stirring agitation is responsible for the increased heat transfer coefficient. So we have here increased heat transfer coefficient. So what happens here, let's say if I have this solid surface, I guess I was showing that before. So let's say these bubbles are forming, and then they grow and they start to detach. As soon as they are getting detached, there's going to be some entrainment of water just replacing that bubble, and that creates a form of agitation and stirring into the system, and that's why we have increased heat transfer coefficient. Now, above point B, like between B and C, where we are above 10 degrees C for water, so the portion of this nucleate boiling BC where delta TE is less than 30 degrees C, greater than 10 degrees C. This is the most exciting part, because that's really the boiling happens and continues. So we have bubbles form in a great rate. The rate is really high that we have forming of numerous continuous bubbles or columns of vapor in liquid. So what happened as we were showing here in this regime, let's say we have the bubbles are forming, but these bubbles are just forming and reaching to the surface. So you see a lot of these columns with many bubbles that are just forming and raising here. So that's the part. Now the evaporation rate reach high value that let's say if you're increasing this delta E, then the evaporation rates are really increasing, and then part of the surface starts being covered by some of these bubbles, and makes it difficult for liquid to reach to the surface. So that's why we reach to a maximum point, a maximum flux at point C. So if you look at this curve, the flux is keep increasing, okay, and delta T is going out, but up. But then when we are reaching point C, we are reaching to a maximum, and that's where we have this Q double prime S and max, or Q double prime max, that we can reach for a boiling process, at least in the nucleate regime. And the reason for reaching for that is the coverage of the surface, part of the surface by the bubbles. So I'm gonna just write down at large excess temperature, we have evaporation rates to reach to the high rate. So we have a very high rate of evaporation, and as a result, the surface is partially covered by vapor bubbles. Now that makes it difficult for liquid, to reach the surface. So as a result of that, so let's say we have this surface that we had evaporation, and now part of this surface is just covered by the vapor. So the liquid cannot really see this part of the solid surface, and that's why the flux, the heat transfer from the surface, is just getting impaired. Like it just stops. Like it can increase really the surface, the flux from the surface to the liquid, because the vapor, if they are just attaching to the solid, they have a lower conductivity and they're acting such as an insulator. So we reach to a maximum for the heat flux. So as a result of everything, what we have here is the heat flux reaches to a maximum at point C. And that's what we called critical heat flux in the boiling process, or CHF, Q double prime max. So nucleate boiling, like what we have here, the regions that we have between 5 and 30 degrees C as a temperature, excess temperature, is the most desirable mode of boiling, pool boiling. And the reason is we have a high heat transfer rate that can be achieved with the relatively low delta T excess, between like less than 30 degrees C. And the whole point here is to deliver heat to the liquid so it can turn to the vapor. So the more heat that we can deliver, the more vaporization, the more boiling we're going to have, the stronger rate of vapor formation we're going to have. And in this nucleation, we can reach really to the close to the maximum, or the maximum We are going to avoid the maximum point I will explain later with the small surface temperature, small 30 degrees C. Beyond this maximum maximum flux, we have another zone that the heat cannot be transferred to the liquid because part of the surface now is really like covered by these vapor blankets or these vapor pockets, and that's why, like, since the heat cannot be transferred, the heat getting absorbed by the surface, and then we have increase of the temperature without that heat being delivered to the liquid phase. So that's the part that we have the transition boiling, which is from point C to D. Now, remember that when we were talking about the nucleate boiling, we said like as the rate goes high, it reached to really like high evaporation, high rate of evaporation, that part of the surface, like some of these bubbles start to stick to the surface, or the surface is partly covered by these bubbles. Now, and that's where we're experiencing this high, the maximum heat flux, that beyond that the flux would decrease, and that happens when a large fraction of heater surface is covered by a vapor film. Not totally, but a large fraction of that is covered by a vapor film. And this vapor film acts as an insulator or insulation. Yeah. Acts as an insulation due to the lower thermal conductivity of, due to low thermal conductivity of vapor. And in this region, both nucleate, like this is the region that both of them exist. So just plotting again the container, and then we are giving the flux here. So what happens is we have a large surface of that, we have this film. Still there are some bubbles, there are some places that bubbles are forming, so still is full of bubbles. So we have both nucleate and film boiling. And film boiling exists. And now when we are looking at this transition regime, like we have here nucleate boiling, and this is getting replaced at point D by film boiling. So what we have here is, we have at point C, we had nucleate boiling. At point D, that's the place that we have film boiling. That's getting replaced by that. Now, generally, we try to avoid operating in this transition regime. We have this unstable film boiling regime, and in practice, we don't operate there. Now, beyond point D is the place that we have film boiling, and that's beyond point D. Here, the heater surface is completely covered by a stable vapor film. So it's a stable and continuous vapor film. And at the point D, this is the place that we reach to the minimum in terms of the heat flux. And that's called, we have the minimum heat flux. The surface is really hot, but the delivery of flux, like the heat to the liquid, is the minimum conditions. And that's the point that we are calling Leiden frost point. Leiden frost point is the phenomenon was discovered by Leiden that if you have a very hot surface, the liquid would, if there is a liquid that is here, it starts just jumping around till it's just getting smaller and getting evaporated. So that phenomena is when the liquid drops on a very hot plate or hot surface, jump around. They don't really wet the surface, it's just around and slowly boil away. So that's the minimum heat flux that we have at point D, and this vapor film that is forming. So in this container, we are reaching to the point that we have this really vapor blanket. This is the liquid surface, and this vapor blanket is responsible for the low heat transfer rate. Now, if you pay attention here, we don't want to stick to this minimum. As we keep increasing the temperature, the flux is keeping increasing too at certain point. And that's the part that the radiation comes into play. So this Q double prime S increases from point D as delta TE increases. And this is due to radiation heat transfer from the surface to liquid through this vapor film. So this is radiation heat transfer from surface, heater surface to the liquid. And it becomes significant when TS just reaches a certain point. Now, in typical boiling process, we really don't see, like if you start doing this experiment and we can't really control the temperatures here, what we see here is we would see there is an increase reaching to point C, and then all of a sudden what we would observe here is a jump from point C to another one called point E. So we really don't see this the decrease of the flux as the surface just goes up. We just see a rapid increase in the surface temperature. So this is in a typical boiling process. So let me just replot that here, just having in front of us. So we are reaching to point C, D, and then up. So C, D, so this is A and B. So what happens when we are doing the experiment? Temperature goes up, reach to the point C to this maximum, and then we see a jump to the point E. And if we want to really generate this transition zone, like from C to D and then E, the power should be suddenly reduced at point C. But that's another topic. Now, when we are increasing the heater power beyond point C, the liquid cannot receive this increased energy. So what happens, like when we are reaching to point C, we said that we are at the maximum heat transfer to the liquid. The liquid cannot get that energy, and this energy is getting absorbed by the solid surface, and that's why we see increased jump to the solid surface from point C to point E. The surface temperature at point E is beyond the melting point of most materials that we are using for heaters. So most heater materials. And at this point, for most of this heater material, if you are passing this Q max, increasing the flux, is we're going to see the rise in the surface temperature, and what you're going to see is burnout occurs. So that's something that you're going to really avoid. So in practice, we generally operate slightly below the maximum flux point. So we are slightly operating below this point C, Q double prime delta T, delta TE. So it's very important to know what is the Q max that we can get.